September 1942, Aberdeen Proving Ground, Maryland. The prototype tank lurched to a stop in the middle of the test course, black smoke pouring from its engine compartment. Major General Jacob Devers stood with his arms crossed, watching as maintenance crews rushed toward the disabled vehicle. That is the third failure this week. The man beside him, a civilian engineer in oil-stained coveralls, did not flinch. I told you the transmission needs reinforcement. I told you the suspension cannot handle the weight. But nobody listens to the mechanic. They listen to the desk engineers who have never worked on a tank in their lives. The engineer's name was William Knudsen, but everyone called him Bill. He was 47 years old, a veteran of the First World War, and he had spent the last 23 years working in automobile factories across Detroit. He understood how machines moved, how metal stressed, how designs that looked perfect on paper failed catastrophically in the real world. What General Devers did not know was that this frustrated engineer had already designed a better tank, a simpler tank, a tank that could be built by the thousands in automobile factories using existing production lines and semi-skilled workers. And what Bill Knudsen did not yet know was that his rejected design, dismissed by Army Ordnance as too simple and inadequate, would soon become the most produced tank in American history and the backbone of Allied armored forces across 3 continents. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The crisis had been building for years, long before that smoking prototype broke down on the Maryland test course. The United States Army entered the 1930s with almost no armored capability. Budget cuts, isolationism, and a doctrine focused on infantry and cavalry left America's tank forces neglected and obsolete. By 1939, when Germany invaded Poland with over 2,000 panzers supported by dive bombers and motorized infantry, the United States Army possessed fewer than 400 tanks. Most were light tanks weighing less than 10 tons, armed with machine guns or small 37mm cannons. They were useful for reconnaissance and infantry support, but utterly inadequate against modern armoured warfare. The fall of France in June 1940 shocked American military planners. German panzer divisions had shattered French and British forces in 6 weeks. The Maginot Line, considered impregnable, was simply bypassed. French tanks, often superior in armour and armament to German vehicles, were defeated through superior tactics, communication, and combined arms coordination. The lesson was clear. Modern warfare required mobile armoured forces capable of rapid offensive operations. Static defences were obsolete. Infantry without armour support was vulnerable. And America had almost no capacity to produce tanks in significant numbers. In July 1940, Congress authorized a massive expansion of military production. The Army requested thousands of tanks. Manufacturers were asked to submit designs. Engineering teams worked around the clock, developing prototypes. But there was a fundamental problem. Nobody agreed on what kind of tank America needed. The Ordnance Department wanted heavy tanks with thick armour and powerful guns. The cavalry branch wanted fast light tanks for exploitation and pursuit. The infantry branch wanted medium tanks for close support. Each service had different requirements, different priorities, different specifications. Design committees argued for months while Europe burned. Into this chaos came William Knudsen, though he arrived by an unusual route. Knudsen was born in Copenhagen, Denmark, in 1895. He emigrated to the United States in 1913 at age 18, speaking almost no English and carrying $8 in his pocket. He found work in a bicycle factory in Buffalo, New York. His mechanical aptitude was immediately apparent. Within 2 years, he was a foreman. Within 5 years, he was managing production lines. He moved to Detroit in 1920, drawn by the exploding automobile industry. He worked for Ford Motor Company, learning mass production techniques directly from Henry Ford's engineers. He helped develop the Model T assembly line, the most efficient manufacturing system ever created. In 1924, General Motors hired him away from Ford. He rose quickly through GM's ranks, eventually becoming president of Chevrolet division. By 1937, he was president of General Motors, overseeing the largest manufacturing corporation in the world. When war broke out in Europe, President Franklin Roosevelt understood that American industrial capacity would be decisive. He created the National Defense Advisory Commission in May 1940 to coordinate military production. He needed someone who understood mass manufacturing, someone who could transform civilian factories into arsenals, someone who spoke the language of both engineers and workers. He chose William Knudsen. In June 1940, Knudsen resigned from General Motors and accepted a government position at a salary of $1 per year. He was commissioned as a lieutenant general in the Army, making him one of the few civilians ever to receive such a rank. His title was Director of Production for the Office of Production Management. His mission was to convert America's industrial capacity to war production as quickly as possible. Knudsen approached tank production the way he approached automobile production. He did not care about elegant designs or advanced engineering. He cared about manufacturing efficiency, parts standardization, production rates, and maintenance simplicity. He visited existing tank factories, studied production bottlenecks, talked to workers, and examined rejected designs that engineers had dismissed as too primitive. One design caught his attention. It had been submitted to the Ordnance Department in April 1941 by the Rock Island Arsenal design team. The tank was designated Medium Tank M3. It was a compromise design, built on the chassis of an earlier tank but with a new turret and upgraded armament. The Ordnance Department had approved it for limited production, but nobody was enthusiastic. The tank had significant flaws. Its main 75mm gun was mounted in a side sponson, not in a rotating turret. This meant the entire tank had to turn to aim the gun, a serious tactical limitation. The design was dictated by manufacturing constraints. American industry could not yet produce turret rings large enough to mount a 75mm gun in a rotating turret, so engineers mounted it in a fixed sponson in the hull. Additionally, the tank had a tall profile, making it an easy target. The riveted construction created weak points where armor plates joined. The suspension was adapted from an earlier design and was prone to failure under combat stress. The 7-cylinder radial aircraft engine was powerful but unreliable and consumed fuel voraciously. Army tankers who tested the M3 called it a death trap. The British, who were desperate for any tanks after losing most of their armour at Dunkirk, accepted several hundred M3s under Lend-Lease, but British tank crews nicknamed it the Grant after Union General Ulysses S. Grant, and complained bitterly about its limitations. American tank officers pushed for a completely new design, something that could compete with German panzers on equal terms. They wanted a tank with a fully rotating turret mounting a 75mm gun, sloped armour for better protection, lower profile, better suspension, more reliable engine, and simpler maintenance. The Ordnance Department created multiple design committees to develop this new tank. Engineers proposed elaborate solutions. Committees debated turret configurations, armour thickness, engine choices, transmission designs, and track systems. Months passed with no consensus. Prototypes were built and tested. Most failed. The smoking prototype General Devers watched at Aberdeen Proving Ground was one of these experimental designs. a tank that looked impressive on paper but could not survive basic field testing. Bill Knudsen watched this process with growing frustration. He had built millions of automobiles using standardized parts, proven designs, and efficient assembly methods. He knew the difference between engineering perfection and manufacturing reality. A tank design could be theoretically superior, but impossible to mass produce. Components could be individually excellent but incompatible in an integrated system. Specifications could be militarily desirable but require tooling and skills that did not exist in American factories. He began, spending time at the Rock Island Arsenal in Illinois, one of the primary tank design facilities. He talked to the engineers, the draftsmen, the machinists. He asked them what could be built quickly using existing manufacturing capabilities. One engineer, James Haw, showed him drawings for a simplified medium tank. The design used as many existing components as possible. The chassis and suspension from the M3, already in production. The engine from the M3, despite its flaws, because it was available. The transmission from the M3, reinforced to handle higher loads. The key innovation was the turret. New casting techniques now made it possible to produce a larger turret ring capable of mounting a 75mm gun in full rotation. The gun would be the standard 75mm that was already in production for other applications. The armor would be cast rather than riveted, eliminating weak points and simplifying production. The profile would be lower, by redesigning internal crew positions. Knudsen studied the drawings carefully. How long to put this into production? Haw shrugged. 6 months if we use existing tooling. Maybe 9 months if we need new equipment. The Ordnance Department already rejected it. They say it is just a modified M3. They want something completely new. Knudsen's expression hardened. The Ordnance Department is not building tanks in factories. They are drawing pictures in offices. This design can be mass-produced. That is what matters. Can it fight? Haw nodded. It is not perfect. The armor is adequate but not outstanding. The gun is effective but not the most powerful. The engine is problematic, but it is good enough, and we can build thousands. Knudsen made his decision. Get me complete specifications, production requirements, and time estimates. I am taking this to the Secretary of War. In November 1941, 1 month before Pearl Harbor, Knudsen presented the simplified tank design to Secretary of War Henry Stimson. He brought no prototypes, no elaborate presentations, just production charts and cost estimates. Mr. Secretary, we need tanks, not perfect tanks. Not tanks that will dominate the battlefield. We need tanks that can be built quickly in large numbers by workers who are building automobiles today. This design uses proven components, requires minimal retooling, and can be in full production within 8 months. Stimson listened carefully. What do the tank officers think? They hate it. They want something better. And if we wait for something better, we will have no tanks when the war starts. Stimson knew war was coming. Intelligence reports showed Japanese military preparations throughout the Pacific. German U-boats were already attacking American shipping. The decision was strategic, not technical. How many can you build? Give me 2 years and access to automobile factories. 50,000. Stimson's eyes widened. 50,000 tanks? 50,000 tanks. The authorization came through in December 1941, days after Pearl Harbor. The simplified medium tank was designated M4. Production contracts were issued to 5 primary manufacturers. Chrysler's Detroit Tank Arsenal, which was still under construction. Fisher Body Division of General Motors in Grand Blanc, Michigan. Ford Motor Company in Dearborn, Michigan. Pressed Steel Car Company in Pittsburgh, Pennsylvania, and Pacific Car and Foundry in Renton, Washington. Additional contracts went to smaller manufacturers for components and sub-assemblies. The production schedule was aggressive. First tanks delivered by February 1942. Full production rate of 1,000 tanks per month by September 1942. Sustained production of 2,000 tanks per month by 1943. These numbers were considered impossible by traditional military manufacturing standards, but Knudsen was not using traditional methods. He was using automobile production techniques applied to tank manufacturing. The key was standardization. Every M4 tank, regardless of which factory built it, used identical major components. Engines were interchangeable. Transmissions were interchangeable. Tracks, wheels, and suspension parts were interchangeable. This meant that parts could be manufactured at specialized facilities and shipped to assembly plants. A transmission factory in Cleveland could supply all 5 tank plants. An engine factory in Michigan could produce for the entire program. This distributed production system was far more efficient than having each tank factory make all its own components. It also made the production system more resilient. If one factory was damaged or disrupted, others could increase output to compensate. The second key was simplification. The M4 was deliberately designed to be maintainable by soldiers with minimal training. The engine could be removed and replaced in the field in under 4 hours. The tracks used simple pin connections that could be repaired with basic tools. The transmission was accessible through large hatches. The suspension used vertical volute springs, a proven design that was robust and easy to service. Combat experience would prove that this maintainability was more valuable than sophisticated engineering. A complex tank that could not be repaired in the field was useless. A simple tank that could be fixed by the crew stayed in the fight. The third key was worker training. Knudsen understood that building tanks required different skills than building cars, but not completely different skills. A worker who could weld car bodies could learn to weld tank hulls. A worker who could assemble transmissions for trucks could assemble tank transmissions. The training programs were intensive but brief. 3 to 6 weeks to convert an automobile worker into a tank builder. Women were recruited heavily. By 1943, approximately 40% of tank production workers were women. They welded hulls, assembled engines, installed electrical systems, and performed final quality inspections. The famous Rosie the Riveter image was based on a real worker, Rose Will Monroe, who built M4 tanks at the Ford plant in Michigan. The production numbers climbed steadily. February 1942, first M4 completed at Lima Locomotive Works. March 1942, 10 tanks delivered. April, 35 tanks. May, 100 tanks. June, 200 tanks. By September 1942, production reached 1,000 per month as scheduled. The tanks went immediately into combat. The first M4s arrived in North Africa in October 1942, just in time for Operation Torch, the Allied invasion of French North Africa. American and British forces landed at Casablanca, Oran, and Algiers, facing Vichy French defenders and eventually German and Italian forces. The M4 tanks of the 2nd Armoured Division and 1st Armoured Division saw their first serious combat against German panzers in Tunisia. The battles were brutal education. American tank crews, inexperienced and poorly trained in armoured tactics, faced veteran German tank commanders in superior vehicles. The German Panzer Mark IV, with its long-barreled 75mm gun, could penetrate M4 armour at ranges beyond 1,000 yards. The M4's own 75mm gun struggled to penetrate frontal armour on German tanks at similar ranges. American tank losses were heavy. In the Battle of Kasserine Pass in February 1943, German forces under General Erwin Rommel inflicted a humiliating defeat on American forces, destroying dozens of M4 tanks. But the Americans learned quickly. Tank tactics improved, infantry-tank coordination developed, artillery support became more effective, and crucially, the losses did not matter strategically because new tanks arrived constantly. For every M4 destroyed, 2 more arrived from American factories. The Germans could not replace their losses. American tankers developed a saying, "The M4 is not as good as a German tank, but we have 5 M4s for every panzer." The saying was only slight exaggeration. By mid-1943, American factories were producing M4 tanks faster than the Germans could produce all types of armored vehicles combined. The strategic mathematics of attrition favored America overwhelmingly. The North Africa campaign ended in May 1943 with complete Allied victory. Over 250,000 German and Italian soldiers surrendered. American and British forces captured or destroyed hundreds of Axis tanks and vehicles. The M4 had proven itself, not as a superior tank, but as an adequate tank available in overwhelming numbers. The invasion of Sicily in July 1943, Operation Husky, involved over 3,000 Allied ships and landing craft delivering 160,000 troops to hostile beaches. The 2nd Armoured Division provided tank support, with M4s landing directly from LST landing ships onto Sicilian beaches. The tanks performed well in the mountainous terrain, supporting infantry advances and reducing defensive positions. The Italian campaign that followed, beginning with the invasion of mainland Italy in September 1943, saw M4 tanks fighting in some of the most difficult terrain of the war. Mountains, rivers, mud, and determined German defenders made every mile of advance costly. The M4's reliability became critically important. Tanks that could continue operating despite difficult conditions were more valuable than tanks with superior armament that broke down constantly. The Italian fighting demonstrated another M4 advantage. Mechanical simplicity allowed field modifications. Tank crews added extra armor plates, scavenged from destroyed vehicles. They welded steel hedgerow cutters to the front hull to break through the thick hedgerows of Northern Europe. They modified exhaust systems to reduce noise. They installed additional machine guns for anti-infantry protection. These field modifications were possible because the M4's design was simple enough for soldiers to understand and alter. The true test of the M4 came on June 6, 1944, D-Day. The invasion of Normandy was the largest amphibious operation in human history. Over 150,000 Allied troops landed on 5 beaches along the Normandy coast. Supporting them were 7,000 ships and landing craft, 11,000 aircraft, and hundreds of tanks. The M4 Sherman, as it was now called by British forces after American Civil War General William Tecumseh Sherman, formed the backbone of Allied armour. The 2nd, 3rd, and 4th Armoured Divisions brought their M4s ashore in the days following the initial landings. Getting tanks onto the beaches proved extremely difficult. Many drowned in deep water when landing craft ramps dropped too far from shore. Others bogged down in soft sand. German artillery and anti-tank guns destroyed dozens before they could leave the beach. But enough survived to provide critical fire support for infantry struggling to break through German coastal defences. The bocage country of Normandy presented unexpected challenges. The landscape consisted of small fields, separated by ancient earthen banks, topped with thick hedgerows. These natural barriers, some dating back centuries, created a maze of enclosed spaces perfect for defence. German troops used the hedgerows for cover, ambushing Allied armour at close range. M4 tanks trying to climb over the hedgerows exposed their thin belly armor to German anti-tank weapons. Losses mounted alarmingly. American tank crews, already aware that their vehicles were outgunned by German panzers, now found themselves trapped in terrain that negated their advantages in numbers and mobility. Something had to change, or the breakout from Normandy would fail. The solution came from a sergeant in the 2nd Armored Division, Curtis Culin. He was a cab driver from Chicago before the war, a man with no engineering degree but practical knowledge of how metal and machinery worked. Culin studied the problem and developed a simple device: steel prongs welded to the front of the tank that could cut through hedgerows like a plough. The prongs were made from German beach obstacles, steel beams the Germans had installed on Normandy beaches to stop landing craft. American engineers cut up these obstacles and welded them onto M4 hulls. The modification worked brilliantly. M4s, equipped with Culin hedgerow cutters, could smash through the bocage barriers, emerging into the next field with guns blazing before German defenders could react. Within weeks, virtually every M4 in Normandy had been fitted with these improvised cutters. The modification was possible only because the M4's simple design allowed field welding without compromising structural integrity. A more complex tank might not have been adaptable. The breakout from Normandy came in late July 1944 with Operation Cobra. American forces concentrated overwhelming firepower on a narrow front, smashing through German lines. General George Patton's Third Army, equipped primarily with M4 tanks, exploited the breakthrough with a spectacular dash across France. In August 1944 alone, Patton's armour advanced over 400 miles, liberating dozens of French cities and destroying multiple German divisions. The M4's mechanical reliability made this advance possible. German panzer divisions, equipped with technically superior Tiger and Panther tanks, could not match the pace because their vehicles broke down constantly. The Panther tank, considered by many historians the best tank of the war, was a maintenance nightmare. Its complex transmission failed regularly, its interleaved road wheels clogged with mud and froze in winter. Its Maybach engine required constant attention. A Panther battalion might have 50 tanks on the roster, but only 20 operational at any time. An M4 battalion with 50 tanks would have 45 or more ready for action. The mathematical advantage was overwhelming. By September 1944, American factories had produced over 30,000 M4 tanks. German factories had produced approximately 6,000 Panther tanks total and fewer than 1,400 Tiger tanks. Even accounting for the superior combat effectiveness of German armour, the numbers favoured America decisively. 5 or even 10 M4s could overwhelm one German tank through coordinated tactics and sheer persistence. American industrial capacity had transformed quantity into its own quality. But the human cost of this strategy was horrific. M4 crews knew their tanks were inferior in direct combat. They knew the German 88mm gun could penetrate their armour at ranges where their own gun was ineffective. They climbed into their tanks every morning, knowing they might not survive the day. The survival rate for American tank crews in Europe was approximately 50%. Half of all tankers were killed, wounded, or captured. These were not acceptable casualties in any moral calculus, but they were the price of America's industrial approach to warfare. The crews developed dark humour to cope with fear. They called the M4 the Ronson, after a cigarette lighter advertised as lighting the first time, every time. German anti-tank rounds penetrating the M4's gasoline engine often caused catastrophic fires. Later models switched to diesel engines, which were less flammable, but the name stuck. They also called it the Tommy Cooker, a British term, or the Burning Grave. These nicknames reflected the reality that an M4 hit by a German gun had a high probability of catching fire. Tank. Crews had seconds to evacuate before ammunition cooked off in explosive chain reactions. Many did not make it out. The veterans who survived multiple tank losses were haunted by memories of friends burning to death while trapped in steel coffins. Yet they kept fighting. They kept climbing into new M4s to replace the ones destroyed. They did this not because they were reckless or because they undervalued their lives, but because they understood what was at stake: the liberation of Europe, the defeat of fascism, the survival of civilization. These were not abstractions, they were real and immediate. Every mile advanced was a mile closer to ending the war. Every German division destroyed was one less obstacle to victory. The M4 was their weapon in this fight, and despite its flaws, it was a weapon they learned to use effectively. The Red Army on the Eastern Front received substantial numbers of M4s through Lend-Lease. Over 4,000 M4 tanks were shipped to the Soviet Union between 1942 and 1945. Soviet tank crews appreciated the M4's reliability and the comfort of its design compared to Soviet tanks. Russian tankers nicknamed it Emcha, a phonetic rendering of M4 in Cyrillic script. Soviet officers praised its mechanical simplicity, noting that Red Army mechanics with minimal training could maintain the tanks effectively. However, Soviet tankers also recognized the M4's combat limitations. The Red Army was simultaneously producing the 34, arguably the best all-around medium tank of the war. The 34 had sloped armor, a powerful 76mm gun upgraded to 85mm in later models, wide tracks for mobility in mud and snow, and a diesel engine. It was superior to the M4 in almost every measurable category. Yet Soviet commanders still valued the M4s because they were reliable and they were available. The catastrophic losses of 1941 and 1942 had destroyed much of the pre-war Soviet tank force. While Soviet factories ramped up 34 production, American M4s helped fill the gap. The Pacific Theater presented different challenges for the M4. Japanese tanks were significantly lighter and more poorly armed than German armor. The Type 97 Chi-Ha, Japan's most common medium tank, weighed only 15 tons and carried a 57mm gun. It was completely outclassed by the M4. In tank versus tank combat, the M4 won decisively every time. But tank combat was rare in the Pacific. The terrain, dense jungles, coral atolls, volcanic islands, and mountain ranges, was unsuitable for large armored formations. Japanese defensive strategy relied on fortified positions, bunkers, tunnels, and caves. The M4's primary role in the Pacific became infantry support, using its 75mm gun to reduce fortifications. Marine Corps and Army tank battalions used M4s extensively in island-hopping campaigns: Tarawa, Saipan, Guam, Peleliu, Iwo Jima, Okinawa. Each island assault featured M4 tanks supporting infantry against fanatical Japanese defenders. The flamethrower variant of the M4, mounting a large flame projector in place of the main gun, was particularly effective against bunkers and cave positions. The psychological effect was devastating. Japanese soldiers who would fight to the death against rifle fire would sometimes surrender when faced with flame tanks. Back in the United States, production continued at maximum capacity. The Detroit Tank Arsenal, operated by Chrysler Corporation, became the largest tank production facility in the world. At its peak in 1943, the plant employed over 25,000 workers and produced M4 tanks at a rate of one complete tank every hour, 12 tanks per shift, 36 tanks per day. The plant operated 3 shifts, 7 days per week. Workers entered through guarded gates, clocked in at time stations, and took positions on assembly lines that stretched the length of multiple football fields. The process was similar to automobile assembly, but on a massive scale. Hull sections arrived from the forge shop, already formed into the distinctive sloped front and angular sides of the M4. Overhead cranes lifted these multi-ton sections onto assembly fixtures, where welders, many of them women, joined the plates with continuous beads. Completed hulls moved to the next station where suspension assemblies were installed. Massive vertical volute springs, road wheels, and track assemblies were bolted into place with precision. The powertrain came next. The Continental R975 radial engine, a 9-cylinder air-cooled design, originally developed for aircraft, was lowered into the engine compartment. The transmission, a synchromesh unit adapted from heavy truck designs, was mated to the engine. Cooling systems, electrical systems, and control linkages were installed and tested. The turret assembly happened on a parallel production line. Cast armor turrets arrived from foundries where molten steel had been poured into sand molds and allowed to cool for days. After cooling, the rough castings were machined to precise dimensions. The 75mm gun, manufactured at specialized ordnance plants, was installed in the turret along with its recoil mechanism, elevation controls, and traverse motors. Ammunition racks, radios, periscopes, and crew stations completed the turret. Finally, the completed turret was lifted by crane and lowered onto the completed hull, where it was secured to the turret ring with dozens of bolts. The completed M4 then moved to the test track, where it was driven at high speed over rough terrain to verify all systems functioned correctly. After passing inspection, the tank was driven onto rail cars for shipment to ports. From Detroit to the port of embarkation, from the port to England or North Africa, or the Pacific, from depot to battlefield, the journey took weeks or months. But the journey always ended the same way, with a 5-man crew climbing into the tank and driving it into combat. By 1945, the M4 had become ubiquitous. It equipped American armoured divisions in Europe and the Pacific. It served with British armoured regiments in Italy and northwest Europe. It fought with Free French forces in the liberation of France. It rolled with Polish armoured brigades and Canadian tank battalions. It was shipped to Brazil, China, and numerous smaller Allied nations. The total production reached 49,234 tanks by the end of the war, nearly 50,000 M4s. This exceeded the production of all German tank types combined. It exceeded Soviet production of all tank types except the 34. It represented an industrial achievement unprecedented in military history. One tank design, mass-produced by multiple manufacturers using standardized components and automobile industry techniques, available in quantities sufficient to equip entire armies across multiple theaters of war simultaneously. William Knudsen, the engineer who had championed the simplified design against Ordnance Department objections, received little public recognition. He remained a $1-a-year man throughout the war, serving without salary or fanfare. He returned to General Motors after the war, resuming his position briefly before retiring. He died in 1948 at age 69. No monuments honor his contribution, no statues stand in his memory. His name is largely forgotten except among industrial historians, yet his impact on the war was profound. The M4 was not the weapon that won the war, but it was one of the weapons that made victory possible. Its availability in overwhelming numbers gave Allied commanders options. They could afford losses, because replacements arrived constantly. They could conduct aggressive operations because tanks were expendable. They could equip new divisions without stripping veteran units. The German military, in contrast, fought with chronic equipment shortages. Panzer divisions were constantly under strength. Replacement tanks arrived slowly if at all. Losses could not be made good. The Wehrmacht fought brilliantly with inadequate resources and ultimately lost because brilliance cannot overcome industrial disparity of the magnitude America created. This was the lesson of the M4 Sherman. Quality matters, but quantity has a quality all its own. The tank that could be mass-produced was more valuable than the tank that was superior but scarce. After the war ended, thousands of M4s sat in depots across Europe and the Pacific, suddenly surplus. Many were scrapped, others were sold to Allied nations. The M4 continued serving in armies around the world for decades. Israel used upgraded M4s in the 1948 War of Independence and the 1956 Suez Crisis. India and Pakistan both fielded M4s in their wars. South American nations operated M4s into the 1970s. Some are still running today, preserved in museums or maintained by collectors. The veterans who fought in M4s carried complicated memories. Pride in their service mixed with grief for lost comrades. Respect for the tank's reliability mixed with bitter awareness of its inadequacy against German armour. Nicholas Moran, a modern military historian and tanker himself, interviewed numerous M4 veterans for his research. He found a consistent pattern in their recollections. They did not love the M4. They recognized its flaws too clearly for that. But they respected it. They appreciated that it started reliably, ran consistently, and could be repaired by the crew. They valued that when their tank was destroyed, another was usually available quickly. They understood that the war was not won by individual tank duels, but by sustained operations where reliability and numbers mattered more than technical superiority. One veteran, Clarence Smoyer of the 3rd Armoured Division, who fought from Normandy to Germany, summed it up. The Sherman was not the best tank, but it was good enough, and we had enough of them. That is what mattered. The M4's legacy extends beyond its military service. It represents a philosophy of engineering and production that remains relevant. Sometimes the adequate solution available now is better than the perfect solution available later. Sometimes simplicity is more valuable than sophistication. Sometimes the ability to manufacture and maintain equipment at scale matters more than marginal performance advantages. These principles apply not just to tanks but to any complex system, medical equipment, infrastructure, technology, and consumer products. The tension between perfection and practicality is eternal. The M4 Sherman was the practical answer to an urgent question. How do you arm your forces when you have limited time, limited skilled labor, and an enemy that will not wait for you to develop the perfect weapon? You design something that can be built quickly, using available resources and existing manufacturing capacity. You accept limitations in exchange for availability. You rely on numbers and logistics to overcome qualitative disadvantages. This is not elegant, it is not inspiring, but it works. William Knudsen understood this because he built automobiles, not weapons. Automobile production taught him that the perfect design that never reaches production is worthless. The adequate design that can be manufactured by the millions changes the world. The Model T Ford was not the best car of its era, but 15 million were built, transforming American society. The M4 Sherman was not the best tank of its era, but 50,000 were built, helping to crush fascism and liberate continents. Today, when engineers debate specifications and committees argue over requirements while problems remain unsolved, the story of the M4 offers a lesson. Sometimes you need to stop arguing about the perfect solution and start building the adequate solution. Sometimes the rejected design dismissed as too simple is actually the correct answer. Sometimes the frustrated engineer who everyone ignores is the one who sees most clearly. Ted Nelson understood this with his welding gun. William Knudsen understood this with his tank. Both men faced the same institutional resistance, the same dismissal by experts, the same insistence on following established procedures, even when those procedures were failing. Both men succeeded by ignoring the experts and building what they knew would work. The next time someone tells you that a simple solution cannot possibly work, remember the M4 Sherman. Remember that the Ordnance Department wanted sophisticated tanks with advanced features. Remember that they rejected the simple design as inadequate. Remember that the simple design went on to equip the armies that liberated Europe and defeated Japan. Simple works, available works. Adequate in large quantities defeats superior in small quantities. These are the lessons written in the production records of American factories and the battle reports of European and Pacific campaigns. 50,000 tanks, hundreds of thousands of workers, millions of hours on assembly lines, billions of dollars invested, tens of thousands of crew members trained, thousands killed in combat. All of this because one engineer looked at a rejected design and said, "This is good enough, and we can build it now." That decision, made in the desperate months after Pearl Harbor, when America faced enemies on two oceans and possessed almost no armored strength, shaped the course of history. The M4 Sherman was not the weapon America wanted, but it was the weapon America needed, and it was the weapon America could build. And in the final accounting, that was what mattered. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.